The next speaker is Luke Harries and Cambridge Center Genomics. And the title of the talk is Neural Networks for Genomic Variant Calling.
Hi everyone, thanks very much for having me. So I'm going to be talking about how we're using some of the fantastic methods we've spoken about already, particularly convolutional neural networks. And we're encoding the genomic data as images, which then allows us to apply these state-of-the-art methods. So a little summary of why we actually want to detect cancer mutations, and then the paper we're building off by Google, which is trying to detect inherited mutations. And so we recreate that, and then we use some of our prior knowledge about this problem to then improve it slightly, and then we translate it over for detecting cancer mutations. So why do we want to detect cancer mutations? Very brief summary, as I'm sure lots of you know this a lot more than me. But effectively, as Cambridge Cancer Genomics, what we do is we translate the sequencing information of the tumour, detect the cancer mutations, and use that to guide clinical insights. So predicting the rate of relapse or which particular chemotherapies we should use for which patients. And so detecting cancer mutations and DNA mutations in general should be really easy. You should be able to take the sequenced tumour DNA, compare that to the normal DNA, and just kind of read along and go, here's the mutation. But the problem is when you're trying to actually sequence the DNA to work out what DNA is at what position. And so we use next generation sequencing because it's much faster and cheaper. So instead of trying to read the entire length of the DNA, which is about 3 billion long, you replicate it lots, you fragment it into these short little fragments, and then you can read the short fragments in parallel. The problem is you then have to piece it back together. And so what you get is something like this. So the reference DNA is kind of what you expect to be at that position. And you get that by sequencing loads of people and then flattening it down. And what happens when you have these fragments, you then align it back to the reference. And the error rate of next generation sequencing is between 0.1% and 10%, depending on how new your sequencer is. So suddenly the problems go a lot harder. You've got kind of what you're expecting the DNA to be, and then you've got kind of these different errors, and you're not sure whether the errors are actually due to a mutation or whether they're an error in the sequencing. So kind of as an example over here is kind of all the same as T with just one error. Then you've got when you've inherited one A from your mum, one C from your dad, or vice versa, and a couple of errors, or you've got it's completely different. So then when we come to detecting cancer mutations, you've sequenced the normal DNA from the patient, and you've sequenced the tumour, and you're then trying to compare these two different matrices. So you've got the tumour reads, you're then trying to work out whether the change at the tumour is actually due to a change due to the sequencing or an actual cancer mutation. And so the problem is that currently people try and deal with this with heuristics, rules of thumb. They say, okay, if it's kind of more than this percentage, then it probably is going to be a cancer mutation. But the data then they use to evaluate these tools is generated by taking normal sequence data and introducing some mutations based on kind of what you'd expect the mutations to look like. So you can start to see it's very cyclical in nature. And so when different tools are produced and use different heuristics, they have very different concordance rates. So the numbers here represent the number that each mutation caller has said this is a mutation. And as you can see, there's some which aren't detected by any of the other mutation callers and some which are kind of high overlap. And so what deep variant's done is they've developed a way of using the huge amount of data there is, encoding it into images, and then training up a classifier using deep convolutional neural networks. And this is for a slightly different problem, the inherited mutations. So with inherited mutations, you have the reference DNA, you have the normal DNA from the patient, and you can say, right, these are where we roughly think the mutations are. And this would be used for something like population-based studies. And so this is our version of, we took what they had done in the paper and we re-implemented it. And the way they actually encode this into an image, is they put the reference DNA at the top of the image, and they replicate it 5 times, and then they insert the rest of the sequence DNA at the bottom. Now, the putting it at the top of the image and the replicate it 5 times, when we were coding this up, we're like, that's a really weird method of doing it. So here's a little summary. We did it, and it works, and it gets in the 90s for accuracy, and it uses something called the ResNet model, so kind of state-of-the-art image classification model. But the problem is, when you're using a convolutional neural net, it applies this kernel over the image. Little animation there. And what the kernel does is it kind of looks at each of the bits of the image in isolation, and it compares the reference to the sequence DNA, and it asks, is there a difference there? But as you can see, as soon as you move away from the top of the image and you're applying your kernel to something around at the bottom, you're not actually comparing your sequence DNA to your reference at all. And so each time you do a convolution, you kind of make the image slightly smaller and try and draw out the key feature. So when you're applying a convolution to the bottom, making it slightly smaller, all you're doing is losing a little bit of information. And so we've created something called the splice kernel. And so the idea is you keep them separate, the reference and the sequence DNA, and instead of just chucking in at the top, wherever you put the kernel, you then insert the reference above and below it, and that way you can compare it throughout the entire image. And so the way we decided to implement that was basically just splicing the two together, hence our naming. And so when you move the kernel over it now, you've always got the reference in the same position, no matter where you're moving around the kernel. So it's much easier to learn the weights. And so to give you a little bit of intuition about this, why this works a lot better, is here's a normal image, and you can see the reference at the top and all the little fragments below. And you're trying to tell that this bit here is different to the reference bit. However, when you splice it together, hopefully some of you guys near the front can see that you end up with actually a dash line in the middle. So it massively draws out where the differences are. And so when we plot some results of this, when we introduce the splice kernel, it kind of gives an increase in accuracy up to 95% from 94%. And also seems to learn a little faster as well. So now, how do we then translate this over to detect cancer mutations? We've now got 2 images, so the image from the sequence normal DNA and then the sequence tumor DNA. And we're wanting to compare them to know whether the change is due to the actual tumor DNA or it's whether it's due to an inherited mutation or random error. And so the problem this is analogous to is it's a verification task. So you're shown one picture of a face you've never seen before and another picture of a face you've never seen before. Are they the same person or a different person? With normal classification, you'd have to require hundreds of images of this person in different lighting to understand that's that particular person, and then you can recognize them again. But as humans, intuitively, we can look at 2 images of different people, even though we've never seen them before, and be able to tell whether it's the same person or a different person. And it's the same with these sort of characters when they're drawn out by different people. Even though you've never seen the character before, you kind of learn a representation of whether they're the same or different. And so this is called a Siamese neural network. And so you pass it through the convolutional neural network, and you get a point in space for each of the images. So our 2 images is one of the sequence normal DNA, and the other is the sequence tumor DNA. And what you train the neural network to do is, if it's of the same type, if there's no mutation, then learn to put them kind of close together in space. And if they're of a different type, i.e. there is a mutation, then learn to put them further apart. And so here's a little summary. And what we do is, instead of applying this to every single site on the DNA, we just apply it to the sites which we initially think, we kind of threshold it, which ones are likely to have a cancer mutation there. And so here's the example of the 2 images, the normal DNA and the tumor DNA, and you pass it in and you end up with a little threshold value at the end. And when we use the ResNet model, we manage to get, again, in the 90s for accuracy with cross-fold validation. So yeah, that's it. Little summary. We took what Google had done with detecting inherited mutations. We then re-implemented this and worked out actually there's something not quite right about the way they're doing it, which gave us a little bump in accuracy. And then we translated this over for detecting cancer mutations. And actually, if you see here, this splice, true or false, is when we introduce the splice kernel again with the Siamese neural network, that again gives us another bump in accuracy. Thanks very much.
Any questions? Two record holders on you. You on the previous talk, or you breaking records. Is that the Google AI? Is it to do with the TensorFlow stuff, or are you using different?
Yeah. So they've open sourced what they had done before, but they've kind of optimized it. Lots of the libraries are in C++ and that sort of thing. So when we were wanting to experiment with it, we translated it over from TensorFlow into PyTorch, which is kind of what lots of the machine learning researchers are now doing. And that kind of allowed us to experiment a little faster. Yeah. Thanks very much.
Thank you.